Hi, I'm Heramb Nemlekar and I would like to give you a quick overview of my work with Yifang Chen, Alex Cuellar, Haipeng, Jignesh and Stefanos Nikolaidis on fair contextual bandits for interacting with multiple users. When a robot has to interact with multiple users, like a social robot communicating with elders or a factory robot supplying tools to workers, the robot has to decide which user to interact with. One way to formulate this is to associate each interaction with a reward, and thus we want to select the user that gives us the maximum reward. However, in a real-world task, the rewards are initially unknown, and the robot needs to explore to learn the reward distributions. This is an instance of a multi-armed bandit problem, where the users are the arms that the robot must pull. However, a previous work has shown that always selecting the optimal user may affect the perceived fairness and trust of suboptimal users in the robotic system. Therefore, it is important to select users fairly, which means that each user should be selected with a minimum rate of at least V, which represents the fairness level. However, previous work in fair allocation does not account for the fact that different workers can be skilled at different tasks. For example, one worker may be skilled at drilling holes, while another worker may be skilled at welding. Therefore, it is also important to select the optimal user based on the context, which in this case is the tool that needs to be operated. Now, let us look at our proposed method for this problem. To incorporate context, we can now formulate this task as a contextual bandit problem with k users, which are the arms, and m different contexts. At each time step t, the environment decides the context from the m total context and the corresponding loss values for the context. The learner, who is our agent, observes this context and selects a user from the k total users according to the history of previous contexts, selected users, and suffered losses. Then, the learner suffers the loss corresponding to the selected arm for that context. Note that the learner is unaware of the loss distribution and we make no assumptions on it. Traditionally, this problem can be solved by using a follow the regularized leader or FTRL approach individually for each context. At each time step, we select the arm which minimizes the past losses, where L hat is the loss estimator, along with a regularization function, where psi is an entropy function to encourage exploration. To ensure fairness, we can define the following fairness constraint. The probability of selecting an arm I for context j at time t multiplied by the probability of the context occurring summed over all contexts should be at least some minimum rate v. This constraint restricts the space of probability distributions over arms to a convex set omega that now satisfies the fairness constraint. Therefore, we can update the contextual FTRL approach to finding the probability distribution from the convex set omega that minimizes the previous losses. We select the learning rate as the square root of m log k by tk, which minimizes the regret of the algorithm, where t is the number of time steps. Now, using the shown learning rate and setting a value of the fairness constraint that is less than 1 upon the number of arms, at each time step, we would calculate the probabilities over the arms from the space omega that enforces the fairness constraint. Then, given the context, we will choose the corresponding arm and finally update the loss estimator for the next step. Now, we will look at the properties of the algorithm and its performance. Consider a contextual bandit problem with two users and two contexts, where the contexts are distributed equally. That is, context J1 and J2 have equal probability of occurring at each round. The loss distribution for each user in each context is given by a Bernoulli distribution, such that user 1 suffers a loss of 1 with probability 0.6 in both contexts, and user 2 suffers a loss of 1 with probability 0.8 in both the contexts. We see that when one user is better than the other in all contexts, where all contexts have equal probability of occurring, imposing a fairness constraint reduces the performance. This is because when there is no fairness constraint, the algorithm would eventually pick the optimal user 1 in both contexts. However, for a fairness level of say 0.45, the algorithm has to pick the suboptimal user 2 with a 45% probability, which reduces the performance. Consider another example with two users and two contexts, where the contexts are again distributed equally. However, user 1 suffers a loss of 1 with probability of just 0.2 in context 1, while user 2 always suffers a loss of 1 in context 1. Whereas for context 2, user always suffers a loss of 1, while user 2 suffers a loss of 1 with a probability of 0.6. We see that when each user is better at a different context, imposing a fairness constraint does not affect the performance. This is because when there is no fairness constraint, the algorithm would eventually pick user 1 for context 1 and user 2 for context 2. As both contexts are equally likely to occur, both users get picked equally. Therefore, even if the fairness level is increased, the performance does not reduce, as there is no need for a suboptimal user to be picked. Finally, we look at the importance of considering context while enforcing a fairness constraint. When we have users that perform better at different contexts, we already saw that the performance of our fair CB algorithm, which considers context, does not reduce as fairness is increased. However, if we ignore the context, then the algorithm would not be able to determine which user to pick for which context, and thus the performance would be the average of the two users. You can refer our main paper for analysis of more simulations for different configurations of users, contexts, and losses. Finally, we analyze the performance and fairness of our method in a study with real users. In order to validate our algorithm with real users, we performed an online experiment where a user from USA and a user from India are paired to answer a quiz. Each quiz had 44 questions. The questions alternated between questions about the states of USA and the states of India, which were the two contexts. We expected that users would be better at answering questions related to their own country. Now, compared to a fair non-contextual FTRL, a fair t-test showed that the fair CB algorithm performs better as it chooses users based on their losses in each context. Additionally, in response to questions about the fairness of the algorithm in distribution questions and the trust of the users in the algorithm compared to the baseline, the rating provided by the users for fair CB on a 1 to 7 Likert scale were not worse than the rating for baseline measured by a non-inferiority test. It was interesting to note that some users were able to identify the fair CB algorithm and its behavior by stating that the algorithm assigned questions according to their countries and assigned questions more evenly. Finally, I would like to mention that we theoretically prove the upper bound on the regret of our algorithm for a given learning rate. Our algorithm achieves regret of big O square root of total time steps t, number of contexts m, and number of arm scale of k, which is equivalent to classic FTRL algorithms. For more details, you can refer the supplementary material of this work. Thank you for your time, and for any questions regarding our work, you can contact me at the email below.